Hello everyone, I'm Wang. I'm a PhD candidate at Civil Engineering Department at Purdue University. So today I'm just going to represent our group to present some of our work on the focus on the sinusoidal helicoidal architecture that to improve the compressive load-bearing capacity of the cement motor. Just some brief introduction. We all use a lot of engineering material in our real world. We optimize the composition. We explore novel manufacturing process to basically improve the efficiency or performance of our engineering materials. However, in nature, there are also a lot of different ways that nature is used to improve the efficiency of the material design, because the animals that in the world have been evolved for 10,000 years. They have their own ways to improve their performance of their own materials. So if we look at, when we design the engineering material, we always want the best performance, of course. However, for our engineering material, there are always some trade-off. Like, for example, for this one, if we compare the fracture toughness with it's a really old HB plot, compare the toughness with the modulus, there's a trade-off. If we want to increase another, we always need to sacrifice another. But for the biological materials, there are some material that can be both stiffer and tougher, which we might be able to learn that from there to keep optimizing our engineering material to improve the performance of that. That brings us to what we are doing is bio-inspired design. Basically, what we can learn from nature. Basically, what strategies or what structures we can learn from there. Like, for example, this is we first identify the functions. We first identify the loading conditions, how the mantis shrimp can smash the shell in a really high speed, or why the the skeleton of the ram can withstand high impact loading. And then we identify the structures and materials, and there are a lot of structures already being explored in the field, like the helicoidal or overlapping or like cellulars. There are a lot of different structures we can use. And then we identify the mechanism. What is the real mechanism behind it, and what we can learn from that mechanism to keep optimizing our materials. So then bring us to the focus of this study, which is the mantis shrimp, which is a delta club mantis shrimp, which is the animal used to smash the shell at really high speed. It's an extreme animal, can deliver really high speed and powerful strike to an object without breaking its own claws or own delta clubs. So that's when we are running. What happened? What's the structure and material in that animal? So if we look at the cross section of the delta club of the mantis shrimp, we can get that it's like a multi-region organ. So this is the microstructure of the delta club of the mantis shrimp, and if we look at that microstructure, can be divided into different regions. The top region, which highlighted in blue, is impact region, and the middle region is periodic region, and then there's another outer region we call the stratic region. So a long time ago, there was a group of researchers run a simulation about the strike behavior of the mantis shrimp of the delta club. They got a stress distribution contour, and if we check the stress distribution contour and correlate with the different region of the microstructure, we can see in the green region where it have the principal stress, it's kind of a Bulliger architecture, which is the layered by layered, but with twisted between each layer. If we look at the top part, which highlighted in blue, which have high compressive stress concentration, it have a helicoidal architecture. So, sinusoidal helicoidal architecture. It's similar to the Bulliger, but it's just featuring a sinusoidal shape, but with rotate between each layers. So each layer have a twist angle, but featuring a sinusoidal shape. So we are running. If we can use this, because nature or multi-shrimp use this architecture to withstand the compressive stress. So we're wondering if we can use this also to optimize the compressive performance of the concrete. And also, this is the previous work done by our group, the real simulation that compared the sinusoidal, helicoidal, and polygon under compressive loading. Because especially if we compare the stress concentration, because the sinusoidal helicoidal architecture have a more uniform stress distribution. We assume this could directly translate to the spread of damage, which is improve of the energy absorption capacity. Also, when we read DIC, we also see a less stress concentration or more uniform stress distribution in the sinusoidal helicoidal architecture. So then we want to explore if we can use this with concrete. And why? Well, of course, under compressive test. Why? Because for 3D printing concrete, we also sacrifice, like based on our result, it's always, especially when you add fibers, because of the present of interface, when we test in different directions, 3D printing concrete under competitive test is always like weaker than the cast element, which is not always good. And because of the present of the straight interface, and the crack are always easily propagate through that, which lead to reduce the compressive strength and also the toughness. If also check the call it work of failure, which is area under the load displacement curve, depends on how you define failure. So for example, if you define failure after a peak load, you can get area under the load displacement curve right before a peak load. Or if you define failure like after your peak load drop by 20%, you can get another like work of failure like calculation, then 40% similar. If you compare that, it's also 3D printed sample regularly, it also sacrifice the work of failure. So if we put everything together, because so we are sacrificing the compressive strength, compressing performance, but we just print regularly because of the presence of the regular interfaces. So it's really important to explore other novel architecture to kind of improve this performance, at least similar to cast level, and also if we can further improve that, so it can perform better than the cast one. So then we come back to the sinusoidal helicoidal architecture. But the problem is how we print. It's featuring a non-planar filament shape. It's not easy to print that. So typically how we print is we print in the X, Y plane, then we switch each layer, build up in the Z plane. But for the sinusoidal helicoidal architecture, we need to have a non-planar filament shape. So we start with we call it 1D because we just have one like dimensional inclined surface. We explore how to print on that support, and then we scale it to print on the regular just one sinusoidal support, and we figure out how to print and how to get how to maintain the sinusoidal shape. However, this cannot twist. This cannot achieve the sinusoidal helicoidal. This can only achieve the sinusoidal. Then we got another two-way sinusoidal support to achieve because this can enable us to twist without influence the overall printing quantity. This we can only achieve the sinusoidal helicoidal by using the two-way sinusoidal support. And just how we design it, if we only follow the sinusoidal two paths, which is the top study, you can see we kind of sacrificing the overall shape of the sinusoidal shape. It's become flatter, flatter, flatter as it builds up. And we try to improve it a little bit by modify the two paths. And using the new two paths, you can see we kind of improve the printing quantities like a little bit, make it a little bit better. Because when we twist, we need to make sure they are maintaining the sinusoidal shape while we rotate, while we achieve the helicoidal architecture. So then after we know how to print, we run the compressive test with different configurations, regular, polygon, and sinusoidal helicoidal architectures. And then we also use the fibers. We also use the steel fibers in the mixture because this is one of our previous study. We found that the fiber, because the incorporated fiber can increase the anisotropic level, because the fiber are really likely to align during the printing direction. This will strengthen the filament without influence the interfacial property that much. This is a strong isotropic, which assumed to contribute to the microcrack development to improve the energy absorption capacity of concrete during the loading condition, during the compressive loading condition. So yeah, you can see from if we compare the 0-degree filament orientation when we do a 4-point bending test, it shows much higher flexural strength and overall deformation or displacement compared to the cast ones and also the 90-degree ones. And it also can get more crack development, get damage delocalization, and also for the 90-degree one, you will just get a straight crack developed through the interface. And this is a strong isotropic we got. So if we look at the compressive test result, so if we compare the regular 3D printing with cast one, we are sacrificing the compressive properties. And if we print with Boolean architecture, which is we did both 5-degree and 10-degree twist angle, which is layer rotate in different degrees. So we notice improvement on compressive strength, and it's like compared to the regular 3D printed one, but it's still kind of weaker than the cast samples. And also work of failure is similar to the cast one, which is good and much better than the regular ones. Because of we can get some, if this is the DIC result we got, we can kind of get some of a twist crack pattern in the sample to basically, it was this longer fracture pattern to improve the energy like required to fill the sample. And if we look at the Sinusoidal Helicoidal architecture, which remember is nature used this architecture to, like in the impact region of Delta Club, to withstand the compressive stress concentration. So we use that to concrete. We can also see, okay, specifically the Sinusoidal Helicoidal architecture in 10-degree is showing better compressive strength compared to the cast ones, even. So it's not only much better than the regular 3D printed one, it's also showing improvement compared to the cast ones. And also the work of failure is also got improved. So by using this architecture, we kind of improve, this is kind of, if we put everything together, we can see if we use Boolean, it's similar to the cast one, kind of consider all the error bars, all the like standard deviation is in a similar region than the cast ones compared to the cast ones. And if we use the Sinusoidal Helicoidal architecture, we can improve both the strength and the work of failure compared to the cast one, and also much better than the regular 3D printed ones. So yeah, this is the kind of the main conclusion. And I want to thank for our team for the providing support, professor providing support for the research, and thanks for the funding agency to fund this research and my travel. Thank you.